And we are back to start chapter 7. So for chapter 7, we will be looking at the formula relationship that exists between chemicals in the same formula. Okay? These are the objectives and the goals of this chapter, so you can go ahead and read that at your own time. I will start with the slide right here, slide 5, talking about the number of atoms in the formula. In the formula, you have two parts. You have the letters. Oops, trying to write with that. Letters. Okay. So within a chemical formula, you have letters. The letters represent the elements or atoms, right? And then you have the numbers. The numbers are usually written as subscripts, and these numbers, aka the subscript, represents the number of atoms or number of elements. So this represents the number of atoms slash elements. Remember, atoms and elements are used interchangeably. Now, the number usually refers to the letters written before. So the number can represent an atom or a group of atoms. So we're told here, subscript numbers are used to indicate the number of atoms or group of atoms of each element in the formula unit of the substance. We usually see all numbers except for the number 1. So the exception is if there is only one atom to an element, then the subscript is omitted. So here we're seeing an example, formula of sodium nitrate. For sodium nitrate, we're seeing NaNO3. By the way, when you're trying to name this, remember, if you have a capital letter or uppercase and lowercase, these most likely refer to the same element. So you're going to, look at this part here in the periodic table, find the name to it. This is a metal. So of course this would be sodium. And then you would name the rest of them together, and this would be nitrate. So just in case, I have a list of, let's see, common polyatomic ions I just found online, and I copied and put them here. So these are actually they are listed, alphabetically. So whatever you're looking for should be here. This is a very comprehensive list, not including every ion there is out there, but a lot of ions. And these are all polyatomics. And once again, they're listed alphabetically. So we have sodium nitrate, sodium, and then this is nitrate. So looking at that, back to the objective, we're trying to count the number of atoms in this formula. So we have sodium, then you have nitrate. So I'm going to break it up like this, right? The 3 belongs to the O. The 1 that's implied here belongs to the N. The 1 that's implied here belongs to the Na. Okay? Remember, they're omitted because of the rule and because they're implied and they're understood. So, as far as the number of Na, sodium atoms are concerned, we only have 1. Number of nitrogen atoms, we have 1. Number of oxygen atoms, we have 3. Okay? So that's how I look at this. They're not asking us to name it, just to go ahead and indicate number of atoms. Once again, as needed, you have this list, which I found online. Feel free to use it. So we're being asked, how many atoms of each element are in the formula unit? So formula unit is a general way of talking about or describing the formula for ionic compound. You have formula unit, you have molecular formula for molecular compounds or covalent compounds. So be aware of that. Okay, so our formula unit is ammonium carbonate. They go about a long, interesting way of naming this. So ammonium carbonate. We're trying to figure out, first of all, what the formula is. Then from there, we'll try to figure out the number of elements in the formula and then count them out and answer the question. So I'm looking at ammonium carbonate. Of course, you can try to find the first word, this element here in the periodic table. You won't find it. So you want to go to the list of polyatomic ions I've provided you and try to find ammonium. So we go to the A's. And there it is, the second one, ammonium. If you try to find the name of an element or what you think is an element and you can't find it in the periodic table, come to this list and this list will most likely have it. Periodic table only has elements that become monoatomic ions, not polyatomic ions, okay? This is why I gave you guys this list. Okay, so back to the question, ammonium, NH4 plus. I'm going to write this on the side. NH4 plus. What else did they give us? They said carbonate. Once again, carbonate is not an element, it's a polyatomic ion. So I look for the carbonate on the C's. Carbonate, there it is. Carbonate is CO3 2 minus. You want to make sure you're very familiar with this list of polyatomic ions. I know it's a long list, but you can take the time to try to be very familiar with this so it's not so much work when you're working on your homework, trying to figure out, is this an element or not? So right here we have NH4, right, plus ammonium, carbonate, CO3, 2 minus. All I got was the ions, right? I need to make it a compound first before I can go through and count the number of atoms. So for ionic compounds, we crisscross these. This comes down here, this comes down here, and then we end up with, since we have a 4 here, we need to put a parenthesis around it to bring in the 2. So I'm going to write NH4, 2. Then here, since I have positive, this is positive 1. The positive 1 is implied. We never write the subscript 1. So I'm just going to write CO3. No need for parentheses because I'm not bringing in a non-1 number. So I leave it as is. I have ammonium carbonate. The question says, find, what was it? Oh, number of atoms of each element. So I'm going to write this out. First of all, I know I have an N, I have a H, I have a C, and I have an O, right? This is showing us that we have 2 NH4s, okay? And so the 2 can be distributed throughout the elements in the parentheses. Therefore, we have 2 N's. And it says we have 2 of the H4s, right? Like that. So when you add them up, you get H8, or the other way of looking at it is 4 times 2 makes 8. So we have H equal 8. You want to multiply the 2 by everything in the parentheses to tell you the number of atoms of each element represented. Carbon, let's see over here. There's nothing down here, so carbon, we just have 1. Oxygen, in front of oxygen, we have 3, so we have 3 oxygens. Okay, so 2 nitrogen, H hydrogen, 1 carbon, 3 oxygen. These are the number of elements or atoms we have in that formula. Okay, they went a complicated way around figuring out what carbonate was. Please use this list. It's more direct and I feel like it's simpler. So we're moving on. Now we're dealing with molecular mass or the mass of molecule. The molecule usually refers to a molecular compound or a compound made up of nonmetals and nonmetals. Formula mass usually refers to the mass of the formula, but what mass? Mass of ionic compounds. Okay, so as far as terminology is concerned, the term molar mass is usually used as an umbrella term to represent both. So molar mass can then be broken down to molecular mass or formula mass. Okay. So when I was taking this class years ago, I didn't know there was a difference. Now here, molar mass, molecular mass, formula mass, and I'll get so confused. I'm like, why are we using so many different terms for the same thing? Molar mass is just the mass of formula. It doesn't matter what type of formula you have. That's what molar mass is, just type of formula. And then formula mass is the mass of ionic compound. An ionic compound usually have metal combined with nonmetal. Molecular mass is usually the mass of covalent compound. And covalent compound is usually not a nonmetal combined with a nonmetal. Okay? So when you see either of these two bottom ones, it's okay to use this top word if you want to. I have seen books use these three words interchangeably. All they want really is the mass of the compound. Okay? So we're told here molecular mass is the average mass of the molecule. Formula mass is equal to the sum of all the atomic masses in its chemical formula. So what we're looking at is just the mass of the elements within the formula. What is the mass of the formula provided? Okay. Now we're looking at this here, and we're told that, okay, we're going to start with, this is carbon and then two oxygens. We're going to start with carbon dioxide. Molecular or formula mass. The sum of the atomic mass of each atom in the molecule is essentially molecular or formula mass. The molecular mass of carbon dioxide molecule is the sum of the masses of one atom of carbon and two atoms of oxygen. So carbon dioxide has one carbon atom and two oxygen atoms. Each carbon atoms weigh about 12. Now the units here depends on the context. The units can either be gram per mole, or I'm going to stick with your textbook so I don't bring about confusion, or formula units. Okay, gram per mole or formula units. So based on what they're showing you here, I'm going to say 12U. Each oxygen atom weighs about 16 formula units. Okay, so 1 times 12 gives us 12. 2 times 16 gives us 32. When we add these two, we get what? 4 units. So carbon dioxide is equal to 44 U's. Okay, or grams per mole. Different units are used for different contexts. When you're working on your homework, you probably have a multiple choice or fill in the blank, and you're going to be using that. Okay. Okay. So now I'm moving on. And here they're saying, calculate the formula mass of ammonium nitrate. Once again, ammonium, we found that before. That would have been polyatomic, not an element. The second one in our list. Nitrate, once again, you go to the end section and find nitrate. I hope it's still here because at some point it disappeared. There it is, nitrate. Copy those two, crisscross, and get the formula. So let me see. Let me get back here. I am going to write my own so I can finish. I can actually work on this on my own page. Okay. So ammonium NH4 nitrate. I get the ions and I crisscross these to make the compound. Since the charges here are equal and opposite, they cancel out, and I can actually bring this close to each other. And O3. Okay, so in the whole compound, I have nitrogen, I have hydrogen, I have oxygen, right? I have 2 nitrogens, I have what, 4 hydrogens, and I have 3 oxygens. Okay, each nitrogen is, let me find my periodic table. I'm not even going to try to use my brain anymore. Each nitrogen is, I mean memory. No, I'm still using my brain, my memory. Each nitrogen is what, 14? And each hydrogen is 1. Each oxygen is 16. So here we're having 2 times 14 is 28. 4 times 1 is 4. 3 times 16 is 48. Let me make sure. 14 times 2 is 28. 3 times 16 is 48. So I add those 2 plus 4, and I end up with 80. Now 80 can be U, okay, approximately U, or 80 grams per mole. We use the unit depending on the context of conversation. Okay, we're now moving on to stoichiometric amounts. Remember, all the math we're doing in this chapter is relationships, mathematical relationships that exist within the chemical formula. We're now looking at stoichiometric amount. Stoichiometric amount that we're referring to here is the part to whole relationship. Okay, for us to get to that, we're going to be defining a unit. The unit used in science to represent a certain large collection of particles is called a mole. Okay. Now, this unit, the mole, represents a large number of items. So let me see. Let me go down here. The mole tends to represent. So when we talk about the mole, one mole represents a large number of items. It could be whatever. Okay. So for us to understand that the mole represents a number, let's start with some numbers, or I would say some terms, some words we're more familiar with, words that represent numbers. For example, if I say one pair, it's understood that one pair, the term pair, stands for two. Okay. If I say 1 week, the word week stands for 7. If I say 1 dozen, the word dozen stands for 12, except for a baker's dozen, which is apparently 13. We don't have that where I come from. We just have regular dozen. Okay, so you have pair. The word pair is understood as 2. Week is 7. Dozen is 2. I mean, sorry, not 2. 12. Okay, I'm gonna make it, y'all. I'm gonna make it. It's just that end of semester burnout. Okay, so the mole represents a very specific number, just like these words here represent a very specific number. What number is it? I'm not going to give you guys the actual full number, just a shortened version. The word mole is 6.022 times 10 power 23 amount of whatever. It's not just well, we see it mostly used in chemistry. That's the context. It's because it's hard to find a number this large in anything else. So we use it mostly in chemistry. You know, my friend and I one time, yeah, we're nerds. One time we're on the phone and I'm trying to tell her, I'm trying to find creative ways to get my students to really understand what a mole is. And she's like, but it's really hard for people to wrap their minds around a mole because the mole is very large. And I'm like, yeah, it is. And so I'm like, we don't even have a mole of people in the world. We have so much less than a mole of people in the world, because people in the world, the magnitude is about billion. A billion is about 10 power 9. You can see the difference between 10 power 9 and 10 power 23, right? There's a huge difference. So it's hard for us to understand, to really wrap our minds around the mole. Anyway, the mole is a lot. So when we're trying to count the particles of the element, we deal with moles. So any amount of any substance that contains the same number of units as the number of atoms in 12 grams of carbon 12 is called the mole. So we are trying to define the mole. And when scientists were able to figure out the amount of items containing the mole, they used a standard. The standard chemical scientists use, standard chemical, to be able to count the number of atoms in the mole was carbon 12. Okay, so carbon 12 is a very specific isotope of the carbon family or the carbon element. You have carbon 12, carbon 13, carbon 14. Carbon 12 is the most abundant. So why they use carbon? Why not boron, beryllium, lithium, hydrogen, helium? Well, the others are either gases or very reactive, so they're dangerous to waste. So scientists realize, hey, carbon is very available. Carbon 12 isotope is very available. It's very stable. It's very easy to work with. Okay, so scientists measured exactly 12.000 grams of carbon 12 isotope, and then took this amount and placed it in a machine And this machine is so this was placed in powerful microscope. Powerful microscope. And with this powerful microscope, they were able to figure out the number of atoms inside 12 grams of carbon 12. Okay? And they were able to determine number of atoms in 12.000 grams of carbon 12. And you can imagine what they came up with, right? They came up with 12.000 grams of carbon 12 has exactly 6.022. Of course, I'm shortening the number, I'm writing the whole number, times 10 power 23 atoms of carbon. So this became the standard. And remember, this atom of carbon is the same thing as 1 mole. So what we can say here is 12 grams of carbon equal 1 mole of carbon, or 6.022 times 10 power 23 atoms of carbon equal 1 mole of carbon. So from here, I want you guys to understand this relationship. This is how I look at it. You have a mole relationship that has to do with the weight amount, which is the grams, or the periodic table mass, and you have a molar relationship that has to do with the counting amounts, this. But you want to have both molar relationships in your list of tools for conversions, okay? So make sure you write this down somewhere. Write down. When you're converting down the road and you need a molar conversion, you're going to be using this. Okay, so practice exercise. Now remember the casually mentioning, right? The mole. They're giving you this information here. A mole of any substance is 6.02. The other 2 is missing, that's okay, times 10 power 23 units of that substance. By the way, this number is called Avogadro's number and Avogadro's constant. It was named after the scientist who discovered it. So let's move ahead and move on to this question here. We're told a sample contains 0.25 moles of ammonia. Ammonia is the formula. It is not common ions or polyatomic ion. So you will have to know its formula. Okay, let me see. Add a page. I have 0.25 moles of ammonia. Ammonia is NH3. This is what's given. How many ammonia molecules is this? Oh man, I don't like when they take such leaps. Okay, I need to explain one more thing. They want us to go from moles of ammonia to molecule of ammonia. So I'm going to give you a little bit of history in my journey. For a while, because we were learning this when I was in middle school, don't feel bad about that. Back at home, they kind of throw you in the deep end and they keep doing so eventually you stop drowning. And then that's how you learn chemistry. I'm serious. We saw it middle school. I'm like, what? And then towards the end of middle school, I was like, okay, I think I'm beginning to get the gist of it. For a while there, I thought mole was the short term of molecule. So I'm like, why are we trying to find something we already have? I'm sorry. I'm laughing at my old self, okay? You can see, right? Okay. Anyway, they're not the same word. They're not the same thing. Okay? So, remember the relationships I gave you? Now I want to make sure I expand on that. I said 1 mole is equal to the mass. So the mass I gave you was for the formula provided, right? So I'm going to say here periodic table mass, because you get the mass from the periodic table, usually in grams, of formula. This is the general form. 1 mole equal the periodic table mass of the formula in grams, or 1 mole equal Avogadro's number, which I gave you as 6.022 times 10 power 23, right? So with this one here is where we have the issue. the word you write in front of Avogadro's number depends on the formula. So let me give you guys a general example. If I say here 1 mole of sodium equal to, I'm trying to explain Avogadro's number, I'll say 6.022 times 10 power 23, and the amounts of, since this right here is an element, the formula here is an element, the word I have to use here, the units that are being counted are actually going to be atoms. So the word atoms go with element. As long as the formula provided to you is an atom, or sorry, is an element, you have to use the word atom. Remember I told you guys earlier that elements and atoms are used interchangeably because the building blocks of elements are atoms. Okay. On the other hand, we use a different word here if you're given a compound. So example, 1 mole of sodium chloride equals 6.022 times 10 power 23 molecules. Okay? Since the type of formula I have here, oops, I changed the wrong thing. So the type of formula I have here is actually a compound, not an element. This is a compound. That means that this, the word I use here, even though the numbers are not different, the word I use here has to be molecules because the building blocks of compounds, in this case, are molecules. So many molecules make up a compound. So the units you're counting when you have a compound is a molecule. The units you're counting when you have an element is an atom. So please notice that. The question they were asking you wasn't difficult, but it's important. Okay? Now that I understand this distinction between atoms and molecules to represent Avogadro's number correctly, I can now go back to the question, right? So here's the question. Let me actually copy this and paste in the next page because for some reason I now feel completely lazy to rewrite that. So I'm going to write this down here. How about that? Paste. Out of focus. There. Okay. So I have my moles of NH3. I'm trying to convert to molecule. Okay. I use my Avogadro's number conversion. 1 mole, and the formula is NH3. NH3 equal 6.022 times 10 power 23. This is a compound. I have to use the word molecule of NH3. Okay? So in my conversions, I will write here 0.25 mol of NH3. Then down here, let's see, I have 1 mole of NH3, and up here I have 6.022 times 10 power 23 molecules. Okay, probably wondering what I just did. So what I did here, I'm going to illustrate it again, is I have to use this equality right here. Like we did before with our conversion factors, the equalities we had before with metric prefixes and stuff like that. We're using that as a conversion factor. So the unit up here must match the unit on the bottom. So I have to have some number mole of NH3, and these have to match diagonally. Well, I'm going to be using this, and this becomes a ratio. So the 1 mole goes in the bottom, and the 6.022 times 10 power 23 molecules of NH3 goes on top. These units cancel out because they match diagonally across. And then my answer will be, and I wrote too big, that's okay. I'm not really trying, y'all. I'm just in I'm suffering from end of semester. It's not really blues. It's just like my brain is like, oh, go on vacation. And then I'm like, no, I can't go. I'm still working. You don't know what it is like where you have to push a little harder. It happens to us teachers too, considering the new semester starts. I need to focus. Oh my goodness. Yeah. Okay. Okay. So I took 0.25 times this, and I get 1 point. Oh, see, this is what happens. No, I pressed something, and then this whole thing just went to the end of the. Okay. I guess even the PowerPoint slides are like, okay, we need to wrap this up. I got 1.5 times 10 power 23. 1.51. So let me make sure. 1.51 times 10 power 23 molecules of NH3. Okay. So this is the answer I get. I think everything looks good. Let me check to make sure that's what they got. Did they even work this out? Oh yeah, this is what they got. Okay, I like comparing my answers with theirs to make sure that they're doing things right. I know I could simply show you what they have on here, but my goal is to be able to work on it with you if you are working on it with me. Okay, so it forces me to slow down so that I can go through the process. Okay, so we are done with this. Check. We're showing it right here. We have talked about how molecule goes with compound versus atom goes with element, right? So these words matter. It took me a while actually to recognize the connection. Okay. This next part here is molar mass. We're now defining the molar mass, which is the same thing as the formula mass, right? Molar mass is the mass of 1 mole of any substance. Just FYI, all the periodic table masses are technically molar masses, even though if it's just an element, they will use atomic mass for element, or molar mass for compound. Like I say, molecular mass for compound, or atomic mass for element. It's still the same thing. They all come from the periodic table. Okay? So it's the mass of 1 mole of any substance is expressed in grams per mole. Remember I was telling you about this earlier? The mass of the element from the periodic table is grams per mole. So when you're using it in this context being conversion, you have to use this unit because that's how it just fits. Okay? The molar mass of any substance in grams per mole is numerically equal to the atomic, molecular, or formula mass. Remember I was telling you earlier, right? Same thing called by 3 or 4 different names. As a young student, many years ago, I was like, can we just stick with one name? Why can't we all just agree on one name? Because it's atomic or molecular or formula mass, same thing. So you want to know what I focus on? Mass. Until I got more comfortable calling it a different name. Mass of the substance in atomic mass units. So sometimes you have atomic mass units. We saw earlier the unit of the masses in the periodic table were units, U. Now we're being told it can also be atomic mass units or grams per mole. So when we're saying the carbon atom is 12, it can be 12 units, 12 atomic mass units, 12 grams per mole. It just depends on how you're using the number. Another thing I had to learn in chemistry, I'm like, why can't we just have like one unit? Why we gotta have all these units? Okay. Hey, I was a student who had asked these why questions. I'm like, why gotta be like this though? Anyway, I got used to it. So don't feel bad if you are like me asking those questions, because the context is different and the purpose is different. And sometimes the role is different. Okay. And so chemists are keen on reconciling differences. Anyway, that's the best answer that I can come up with. Atomic mass for carbon 12, if they're asking atomic mass, you will provide your answer as 12 atomic mass unit. If they ask you for molar mass, 12 grams per mole. If it's a free response, write whatever you feel works for you. But if you're working on your homework problem and the answer unit has either this unit here or that unit, just go with it. Okay, the most important thing at that point is your answer. Okay. Okay, we're told to calculate the mass of calcium fluoride. So calcium is an element. Fluoride is also an element. I recognize this as an ionic compound. Why? Calcium is a metal, and this is a non-metal, so it's an ionic compound. So I have to make ions of this. Calcium is in group 2, plus 2. Fluorine is in group 7. The charge is going to be -1. Okay? Crisscross these. That's what you do with ionic compounds. This 1 disappears down here, and we get CaF2. Okay. So you see how they do? Okay. In the formula, we end up with 1 calcium, just one of these. And then we end up with 2 fluorines. Oops, I said 2 fluorines, and I'm writing the word out. 2 fluorines. The calcium is what? You look at the mass in the periodic table, it's 40. I know it's written right here. I'm going to use an abbreviated form. Fluorine is 19. So we have 40 here. We have 38 here. When you add this up, you get 78. And this is going to be grams per mole because they're asking for molar mass. Okay, you're not doing free response. That's the good thing about this class. You're not doing free response answers where you're just trying to figure it out. Online, you're having to show your work, but then the units are provided for you. Okay. Okay. Then here we're going back to the conceptual. Exactly how does 1 mole look? If you walk into the lab, can you actually see a mole of a mouse? Okay. Yes, you can. And they gave you different variations here. They're showing you what 1 mole of different elements look like, what 1 mole of a molecular compound looks like, and what 1 mole of an ionic compound looks like. How does it look? Different. I know. I'm like, okay. Okay, so let's look at this. Let me see. Oh, okay. Without really having, I mean, the title here is somewhat, okay, I see. The title here, they could have written this word down here. So the one on the left, these are all elements. And we have 1 mole of the elements, of each element represented, right? On the right, we have 1 mole of compounds. But they made it a point to give us 2 different types of compounds. We have some that are molecular. Remember, molecular means non-metal. And then we have ionic. Ionic is metal, non-metal. I'm going to say it so much so hopefully you can hear it over and over, right? Okay, let's examine our elements on the left. We have, to the left, drum roll, we have nitrogen gas. Remember, nitrogen is part of the Brinkerhoff family. Brinkerhoff, right. So by itself is N2 and it's a gas. So it takes about 28 grams of nitrogen to make 1 mole. When it says grams per mole, it's saying in 1 mole of nitrogen, you have 28 grams. Or to get to 1 mole of nitrogen, you need to measure out 28 grams. Okay, so this is going to be an interesting looking balloon. Okay, so inside that balloon, they have pumped in 28 grams of nitrogen. So that's check 1. Over here, you have iron. And iron takes a little more to get to 1 mole. To get to 1 mole of iron, you need to weigh out 55.85 grams. Okay. And once again, what all of these equal when you put them in the very powerful microscope and you count the number of atoms you have. Remember, you end up with Avogadro's number, which is 6.022 times 10 power 23 atoms for all these on the left. On the right, you end up with, again, Avogadro's number, but these are compounds, so it would be 6.022 times 10 power 23. You can't use the word atoms because they're compounds. You will say molecules. Okay. Okay. So here, 55.85 grams of iron are required to get to 1 mole. Mercury is a lot more. With mercury, you have to get 200.6 grams of mercury, this amount here. So that all the particles in here, all the little particles, add up to 1 mole. And then we have, copper. I was about to say, this is not copper. We have copper. Okay, y'all, this doesn't look like sodium. Sodium is a metal. Okay, listen, I don't know. This picture is not my picture. I don't know what is going on here. This looks like sodium chloride, if you ask me. Okay, sodium is a metal, and it doesn't look like a salt. This looks like a salt. Okay, so imagine this was sodium, and if it was sodium, it would have to weigh about 23 grams of sodium to get to 1 mole. For copper, 63.55 grams to get to 1 mole. Then on the right side, we have these right here. On the right side, copper sulfate, ionic solid. Oh, not just copper sulfate, the one that's crystallized with 5 waters. It takes 249.69 grams of copper 5 sulfate. Sorry, copper 5 to get copper sulfate with 5 waters, which is actually copper 2 sulfate with 5 waters. So copper 2 sulfate pentahydrate. I'm saying this so fast, right? Okay, I'm going to slow down a little bit. Copper 2 sulfate pentahydrate. It takes 249.69 grams to get to 1 mole. With mercury 2 oxide, it takes 260 to get to 1 mole. Once again, with water, it takes 18 grams to get to 1 mole. With oxalic acid, I'm trying to think, why did I use this acid here? It's not very, but anyway, organic acid here, it takes 90 grams to get to 1 mole. And then we have oxalic acid dihydrate. It takes more mass to get to 1 mole because each individual particle is much larger, so it weighs more. You get the idea, right? The compounds use the term molecules to describe the individual units. With elements, you use the term atoms to describe individual units. Okay, finally, you are carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of the compound do you measure out? Okay, let me go ahead and add my page right here. So, barium chloride. I look at the periodic table. Barium is an element, it's a metal, right? And it's in group 2, so I write its charge. And then it said chloride. Chloride is a nonmetal in group 7, so I put in the charge, -1. Okay, give me just some, oops, pour some water. Okay. So as I'm working on this here, let me dab. As I'm working on this here, I need to get my compound. Hold on, I just have a couple of drops. Y'all can't see anything. I'm just seeing stuff on my end. Okay, crisscross to get the compound. This goes down here. This goes down here. We get barium Cl2. Okay. Now the next question is, what's the, oh, how much do you weigh? Okay, so we're given 0.036. This is 0.0360 moles. Okay, and they're asking you how much does it, or how much should you weigh to get this amount in moles? In other words, convert this to grams. Okay, let's see. I need to get mole to gram relationship. So I go back to the mole relationship, and I have 2. 1 mole of barium chloride is equal to 6.022 times 10 power 23. Since this is a compound, I'll use the word molecule. They usually use the word molecule or formula unit. The other molar relationship I have is 1 mole of barium chloride, and this is equal to the mass of barium chloride. Okay, I need to do this on the side. 1 barium is equal to 137.33. I have my periodic table right here. And then each chlorine is 35.4, where is it? 53. So let me go ahead and figure out the mass, the molar mass of barium chloride. 137.33 plus 35.453 plus 35.453. Okay, so I end up with 208.2 grams of barium chloride. Okay, so I'm going to set up my conversions, right? I have 2 mole conversions to pick from. I can pick the top one or the bottom one. So I'm going to start with this. If I start off with 0.0360, I start off with what's given, moles of barium chloride. Oh, let me write this differently. MOL. Because I want the letters to match, okay? Do they have to match? No, they have to mean the same thing, though. Okay. It's those small things. Okay. So we got this right here. Since I have mole up here, whatever I have down here, the unit has to be mole. We got that. But I have two moles to pick from. Which one do I use? Will any of these moles get me to my desired unit, grams? Yes, the second one, because this second conversion relates the mole unit to a number that has a gram unit. So you want to use this whole conversion right here. Okay, 1 mole of barium chloride, goes with 208.2 grams of barium chloride. Okay, so I have my number times 0.0360, and I get 7.496 grams of barium chloride. So what they're saying here is you can get to a mole by either counting atoms, which you can't even see atoms. So the idea of counting it to get to the mole is a dream. Theoretically, it sounds like it can be done, but it's very difficult to do it. The easier way to get to a molar amount of substance is by weighing. Now here they're telling you if your goal is to get to 0.0360 moles of barium chloride, how can you get to that number by weighing? How much would you want to weigh? Well, you want to weigh this number here. If you weigh 7.496 grams of barium chloride, the particles in there equal 0.0360 moles of barium chloride. Okay? Well, they rounded theirs up, but you get what I'm saying, right? These moles here, the mass here, if you were to count the number of molecules in that mass, you will get these here, these moles. If you're trying to find the moles, right, you find these moles of that substance, okay? So now they have a relationship between conversions amongst mass, amount in moles, and number of units. So here we're being told the mole is the connecting link between macroscopic world and particular world. You know what's funny? I skimmed over this earlier. I didn't see the statement. This is such a deep statement, y'all. It's such a deep statement. The mole is the connecting link between the macroscopic world. The macroscopic world here is referring to mass. We can see things if the masses are large. And then the particulate world, which is the atoms. We can't see that. We cannot see this. So, wow, the mole is the connecting link between the particles we know exist but we can't see, and the amounts that are measured in the lab that we actually can see. Now, the way I see the mole is like a mixed master, right? Which I learned that term when I came to America. Some highways have mixed masters. So I may not be saying this correctly. Bear with me. I was told. Okay. Because I was like, what's a mixed master? And it was explained to me, okay, that there are all these highways that intersect, that's my version of it, at certain points. And the points where all these highways seem to intersect, not necessarily run into each other, but they kind of, all converge at this point, that is the mixed master. Now, this may not be the best illustration of the mixed master. And if you know better, go with that, okay? I feel like downtown has a lot of mixed masters here, right? At so many points. You have so many roads kind of winding into each other or kind of intersecting or bypassing or driving above or below each other. But you see a lot of mixed masters happening in downtown, right? So for many conversions, when we get to the mole tends to be one step away from the mass. So you see here, they're showing you can start with so many different units. As long as you can convert to mole, you can get to mass. because the mole is always one conversion away from the mass. Okay? They're showing you this. You can start with maybe the number of molecules. From molecules, you can convert to mole using Avogadro's number. From mole, you can convert to mass using the periodic table conversion. They're telling you that's possible, right? The other path that's possible is the reverse, starting off with the mass, knowing that from the mass you can convert to moles, because moles, between mass and moles, you just have one conversion apart, right? Once again, using the periodic table conversion, from moles you can convert to any other unit. And the unit can be, I guess I'll say, molecules. I don't want to go outside the bounds of what we're discussing right now. Okay? And so they use MM to stand for molar mass or periodic table mass. I use PT for that. So PTMM, same thing. And this is Avogadro number. Okay? So let's go ahead and start to see how this plays out. We're being told here, once again, if your goal is to go from this starting point, a measured macroscopic quantity. When they say this, it sounds so vague. What are they talking about? Macroscopic tends to be the things that we can experience in our world. So the way I look at this is just a measured quantity in lab, something that you measure in lab, right? What kind of measurement can you make in lab? A bunch of different measurements. If your goal is to go from that measurement, the number you got and the unit, and you're planning to convert that to a particular quantity, particular refers to the amount in atoms or moles, then this is of course your goal, right? Goal. Then what you want to do is you want to take your mass in grams, if this is your starting point. Once again, the mass in grams is something that you can actually measure in the lab. You see how much easier the next picture makes the first picture? I mean, because I'm looking at this saying, once again, it took me a while to get less overwhelmed by the level of vagueness. Okay, this is, I probably am not saying it correctly, but chemists can be very vague. Okay, I just happen to be around here for a while, so vague, I can use the context to fill in the gaps. So you can measure the mass of a chemical in grams in the lab. You will use the molar mass to go from the grams, and then you will get 2 moles. You can't go from grams directly to number of particles. Okay, you have to go from grams. You will then convert to moles using molar mass. And then from here, you will use Avogadro's number to convert from moles to the quantity of particles, depending on the formula. They're trying to remain non-committal here. So this could be either atoms, if it was an element, or molecules, if it's a compound. Okay? Yeah, I know I'm giving a lot of dialogue, but remember, this information means something, so we can't just gloss over it. You have a choice now, since you're listening to me in a recording, to fast forward. Hey, that's your prerogative. But that stuff is there for a reason, okay? Okay, practicing. It says here, practice exercise 3 of 3, determine the mass in grams. So our goal is to get in grams, to get 2 grams, okay? Here, determine the mass in grams. So what is wanted? Our goal is to get some number, grams, of, okay, you see the top part. And what is given to us? We're given 3.2 times 10 power 24 molecules. I'm expecting the compound because of the term molecules, right? Of sulfur tetrafluoride. Sulfur tetrafluoride. Okay, tetra referring to 4. Yes, in this context, tetra is 4. It's not quad or anything like that. It's or yeah, that's the prefix they use here. So sulfur tetrafluoride. This is correct. Molecules go to the word compounds. So we're given the molecule and we're asked to get to grams. You can get from molecules to grams directly. You have to go through moles. So for here, when you see the term molecule, think moles. Even though they're not the same thing, they're usually just a step apart. So when I see the word molecule, I usually write 1 mole equal 6.022 times 10 power 23 molecules of SF4. Or 1 mole equal, what's the other one? Grams of SF4. I need to find out what S is. From periodic table, S is 32.066 grams. F is, I'll say 19 grams. And we have 4, right? So let me do the side math real quick. 32.066 is F plus 4 times 19 close parentheses, and I get 108.1 gram. This should suffice. So from here, because I saw the word molecules, and for the most part in your calculations, molecules, usually if you're going to do some kind of conversion from molecules to something else, most of the time you need the molar conversion. So I usually try to write both of them, and I use whichever I need, right? So I wrote the conversions for moles in terms of the formula provided. Since the formula is a compound, I have to use the word molecules with Avogadro's number. And then here I found the mass by adding 1 sulfur to 4 fluorine, so I have that. Now I'm about to set up my conversion. You always start with your given number. Your given number drives everything else you do. So 3.24 times, 3.2, just 3.2, right? Times 10 power 24 molecules of SF4. Let me make sure it's 3.2. Yeah. Okay. So since I have this here, my conversion has to have the term molecules of SF4 below. So I look at my 2 possible conversions. Okay, I'm looking for the word molecules of SF4. There it is. So this is the conversion I have to employ next. And the part that has molecules of SF4 has to be on the bottom. So, oh snap, 6.022. I need to move this over. I was trying to be presumptuous. It's okay. Oh snap. Do I have enough space? No, I'm going to have to do this again. Okay, let me move this over. Okay, I need a space. I need the space, and I'm trying to conserve times 10 power 23, right? Okay, so I just use this one here, and I write here 1 mole of SF4. So here's the next thing. Are we going to mole? No, they want us to go all the way to grams of SF4. So I'm not done with my conversion. I have to use one more conversion. Since the top one is done, will the bottom one suffice? I have the units here cancel. I have 1 mole on top left over, so I'm going to use mole on the bottom, SF4. So I need a conversion that has mole of SF4 in it, or at least mole. That's going to be this number here, or this conversion here. 1 mole of SF4 goes on the bottom, and on the top we have 108.1 gram of SF4. Okay, let's do our math and see what we get. Oh, no, I'm just trying to, oh yeah, I was trying to make this, okay. Trying to make this smaller. Can I make it smaller? Oh yeah. Yeah, it's hard for me to write that small. Okay, open parentheses, 3.2 exponent 24 times 108.1 divided by 6.022 exponent 23. 23, did I get 23? no. Delete. Go to the right, then down. Okay. Okay, showing here that I have 574.42 grams of SF4. Let's see. So about 570 grams of SF4. Let's see what they got. Oh, yeah. So they use scientific notation, but they got the same answer. It's 2 sig figs. It's been so long, right? But this is 2 sig figs. So our answers have to be rounded up or down to 2 sig figs. Okay. Okay, now we're looking at mass relationship amongst elements in a compound. Okay, so for this part here, we're looking at the part to whole relationship. And we're told that within a compound, since a compound is made up of elements, there is a relationship between the elements and the compound. So we're told that percentage composition of a compound helps us to find the amount of any element in a known amount of a compound. Percent is the amount of one part of a mixture per 100 total parts in the mixture. What? Okay, when I say percent of the element, usually the part over the whole times 100. So percent of the element, which you need to know, is the part, the same unit. So if we're dealing with mass, right? Part in grams over whole in grams times 100. So example, because this is what you're responsible for, percent of the element. Calculate the mass percent of fluoride in calcium fluoride. Okay, so let me bring in my page here. Add a page. Add a page. So calculate the mass percentage of fluorine in calcium fluoride. So calculate. Oh, now I can't spell. Can't. Woo-hoo. Calculate. We're trying to figure out percent fluorine, right? That's what it says here. And it says not just percent, but a mass percent. So the part over the whole is going to be in grams. Yes, mass percent, just like that. And so our part is fluorine in calcium. Calcium is 2 plus. I'll just write the formula because y'all will figure that part out. Calcium fluoride, correct? Okay. So let me see. Percent fluorine and calcium fluoride. Let's do this. So our part is obviously fluorine, and our whole is calcium fluoride. So let's take the whole and break it down into parts. Calcium fluoride is made up of calcium and fluorine. Calcium, we have only one atom, and each calcium weighs 40.08 grams per mole. Okay? Fluorine, we have 2, and each fluorine weighs about 19 grams per mole. So we're just doing a generic one, right? They didn't give us a mass. Okay, we'll do that. 40.08 grams per mole. Over here we have 2 times 19, 38.00 grams per mole, sticking with the same decimal places. Okay, our total calcium fluoride equal, you add those two, plus 40.08, and we have 78.08 grams per mole. Okay? Once again, this is our part. This is our other part. I guess if you want, you can say part 1, part 2, and this is a whole. Okay? Since they want us to find the relationship between this part and this whole, then we're going to say our percent fluorine is going to be, oh, hold on a second. Our percent fluorine will be 38.00 grams per mole over the whole compound. So it's like saying this is fluorine's contribution to the mass of the whole compound, right? 78.08 grams per mole, and of course times 100, right? The part over the whole, remember this is the part, this is the whole, divide that out times 100. So the part here is 38.00 divided by the whole 78.08 times 100. We get 48. So fluorine contributes 48%, 48.7% of the mass. Right. Even though we have two fluorines, both fluorines don't even equal half. They're close to half, but they don't equal half of the mass of the whole compound. Okay? This is what they get. Same thing, right? So you can see it's a part and whole relationship. Chemistry has a lot of part to whole relationship. If your journey with chemistry doesn't end here, you will see a lot of that. Okay? It's like watching, as I said, chemistry really was very appropriately named. Okay, chemistry. It's like watching a TV series where the plots have familiar twists, and you're like, oh, we've been here before. I kind of know where this is going, right? When you're studying chemistry, there are familiar plots and twists in the method that we're using in the calculation. So there's a lot of part to a whole relationship. So while we're here, there is a part to whole relationship that has to do with mass, and it's like part, like I'm in a role trying to explain something and I misspell it and I have to go back and correct it. That's okay. Part to whole relationships, right? Where the part is measured in grams, like I mentioned, the mass percent, or we'll see later on where the part is measured in moles and the whole is also measured in moles. Usually when you have a part to whole relationship, the units of the top and the bottom have to match. I have even seen part to whole relationship where the part is volume and the whole is volume. Whole. Y'all excuse me. Bear with me. Okay? As I bear with you. These spelling things. Okay. Part to whole relationship. Right. So you can have mass, you can have moles. I have even seen volume, but they're all just different part to whole relationship that depend on the context. Okay? Okay, continue. So here we're told, calculate the percentage composition by mass of aluminum sulfate. They didn't say what element, so we have to do all the elements. Okay, we can do this. We can do this. Since they didn't specify which element, we're going to do them all. As soon as I can get out of this little menu thing, it's the small things. Aluminum sulfate. Man, they chose an element. That's okay. They're trying to make sure they work our brains. Okay? Okay, we can do this. So aluminum sulfate. Am I back in? Okay. Aluminum sulfate. Okay. So we have our aluminum, right? And we have two aluminums because the 2 belongs to aluminum. And each aluminum is worth how much? It's in group 3, period 1, 2, 3, 3. We want to round this up, 27. I'm going to round this up, okay? You can use gram per mole or just gram. Either one is fine. I'm going to round mine up. Or I guess I should stop being lazy because I have the period table right here. Okay. 26.98 grams. So I'm done with aluminum, right? We have 2. And then we have sulfur. And sulfur, let's see. I'm actually thinking about moving this further left. Let me see. How do I do this? Let me move this a little left. And then I'm going to write this below. So this is aluminum. And then in the same formula, I have sulfur. And sulfur, we have 3 sulfurs. Remember, the 3 gets distributed into the elements in the parentheses by multiplying the 3 on the outside by the subscript that currently exists in the parentheses, right? So sulfur is going to be 3, because it's 1 times 3, and each sulfur is 32.066 grams. Okay, then moving on. Oxygen, 4 times 3, right? So we do have a lot of oxygen. 4 times 3 is what? 12. And each oxygen contributes about 16. That's where I draw the line, 16 grams. Okay? So let's see the contribution of each of these elements as part of a whole compound. From aluminum, we get 2 times 26.98, 53.96 grams. And from sulfur, we get 3 times 32.066, which is going to be 96.198 grams. And from 12 oxygens, we get 192 grams. So before we add this up, you can see which element contributes the most, right? Okay. So when we go ahead and figure out the total, our total here is for aluminum sulfate. Oh no, this is right. Our total weight is, you just add these 3, 192 plus, let me see, can I write this answer here? Plus, can I be lazy about this? Let's see if it'll work. That, plus, I'm just pulling down the previous numbers I wrote. Okay. Yay, let's see if this will work. Okay, it shows I have 342.158 grams. Let me make sure this is correct before I continue to 42. Okay, I'll take that. Okay, so remember, these are all parts. This is part, we can call this part 1, part 2, part 3. But the idea is the compound is made from 3 different elements, each one contributing a certain percentage. What is that percentage? Take the part mass, divide by whole. We have the whole down here. So take this number, divide by 30, 342 point, I'll say 2 grams times 100. The part over the whole times 100. That gives us a percentage, right? Part over whole times 100. Times 100. Oh, we don't have a lot of space down here. We'll squeeze it in there. Times 100. And what do we get? Okay. So for 53.96 divided by that times 100, I get, oops, that's a pen, 15.77% for my first one. My second one, how do I write this here? Let's see. I'm trying different ways of working this out to keep my brain actively engaged. Okay. So 96.198. Will they allow me to insert this? Divided by, I discovered something new, times 100. Okay. 28.11%. Okay. And then down here, let's see, 192 divided by 342.2 times 100. Ta-da! 56.107. Okay, I have to round these down. So let's see. The numbers they gave us were what numbers in the beginning? Did they give us any number at all? No. Okay, so we can round this out to whatever decimal places we want, but we have to be consistent. So I'll say 1, 1, round this off, and this should be okay. 15.77, yes. 28.11, yes. 56.12, yes. And when you add all three, when you add part 1 to part 2 to part 3, look at what you get. 100%, because they're all parts of the whole, and the whole is 100%. Okay, we're doing good. We're doing good, guys. Okay. Oh, okay. So here they have us using the part to whole relationship. Okay. It wasn't introduced, so I'm going to go ahead and introduce it because they have a knack for that, not introducing it. Okay. I'm going to introduce this section here. Sidebar. They're using part to whole relationship as a conversion factor. Okay, let me tell you something about chemists, okay, that I've realized. Okay. This is a group I'm part of. If they can use any kind of relationship that can be written as a ratio, as a conversion factor, they will. They use relationships to convert from one form to another. So the part to whole relationship is usually written as a ratio. So if it's a ratio, it can easily become a conversion factor. So here we're looking at aluminum chlorate. So the assumption here is you have the formula for aluminum chlorate. Okay, let me add a page below here. And aluminum chlorate is aluminum chlorate, like that. Okay. Aluminum chlorate is 38.35% chloride. Is 38.35% chloride? Chloride. Okay. What mass of aluminum chloride is needed as a source of? Okay, hold on. What? Okay, we're looking for mass, right? So I should write the whole question. That's necessary. Wanted grams of aluminum chlorate, not chloride, chlorate. I'm trying to correct myself here. So what mass of aluminum chlorate is needed as a source of 50 milligrams chloride? So this is our first given. This is a very interesting written question. This is our first given. So I'm going to write it as it's written. Okay. Then they're telling us what's wanted. And they're giving us another given. So I'm going to make this a given 2, which is 50 milligrams, 50 milligrams of chloride. Okay. So looking at these numbers here, you have 2 givens and you have 1 wanted. I usually have my givens together and my wanted by itself. So what I'm going to do here is bear with me as I move this over. Can I move that over? Oh, okay. Let's just put it apart. Okay. Now I want to move this up here. I like these together, the givens together. Okay, there. So my given 1, my given 2, and I have my wanted on the bottom. Let me move this over. So I actually just need the space. Plus, I like to use these features. When else do I get to use them? Okay, there. So I have my first given, I have my second given, and I have my wanted. Now here's the question. When we're given one given, when we're provided with one given, we usually start with that one given. But now we're provided with 2 givens. So which given do we start with? Here's a little note to you, a reminder. Start with the simplest given. Given. Okay. Start with the simplest given. Okay, well, what is simple? Is this number simple or is this number simple? In this context here, simplicity is relative. Okay, milligram will be the simpler one because it's not a ratio. When they talk about simple, they usually mean like it's not something over something or it can't be made into a ratio. A percentage is technically a ratio because it's a part over a whole. So percentage is more complex because it's a part over a whole. So start with this. Start with this. Okay. So you're going to write 50.0 milligram as a starting point. But before I continue with that, let me actually go back and decode the percentage. We need to decode percentage first. So to decode the percentage, I'll write here 38.35% has to be decoded. So imagine I told you you got 38.35% on the exam. You're like, what? What do I mean? I mean you got 38.35 over how many possible points? Over 100. That's understood. So all I did now was convert the percentage into a part to whole relationship as a fraction or the ratio form. Okay, what's the part here? The part is chloride. So this is going to be chloride. And then the whole is this whole compound, aluminum. I just write the formula, aluminum chlorate. I was going to write the whole word, but that should work. Okay, let me see. They use a symbol or the whole word? Oh, they use just a symbol. Okay, fine. So for chloride, I'll use Cl so as to not be confused. I always use the Cl minus. I just leave that Cl since they use Cl, even though chloride is technically Cl minus, but I'm going to use what they use. Okay, so the part to whole relationship, if you had 100 grams of aluminum chlorate, you would have 38.35 grams from chloride. But since they give you the conversion or the number here in milligrams, all you need to have in this ratio is matching units. So I'm going to squeeze milligrams here and milligrams here, and ta-da, my conversion works. Since the percentage did not really define what the unit was, feel free to use the units as long as the top unit matches the bottom unit. Okay, now I'm going to start. Now I'm ready to start with my given. My given is going to be 50.0 milligrams of chloride, Cl, right? Use your conversion. And then let's see. I have to have milligrams of Cl on the bottom. That's pretty much this top part here. 38.35. I just flip this. So I'll say flip this, referring to flip that. Sorry for my bad drawing. Flip this. So I have 100 milligrams of aluminum chlorate. Okay? Milligrams of chloride cancel out. All you're doing now is multiplying the top number. So the top number is 50 times 100 divided by 38.35. And we end up with 130.38 milligrams of aluminum chlorate. Okay. So let me see what numbers we had. We had 3 significant figures here. So I need to round this to, oh, you can use, what is it called? Scientific notation. Be 1.30 times 10 power 1, 2. 10 power 2 milligrams of aluminum chlorate. Okay, let me see what they did. Yeah, that's what they did. They did this way. Because if you do it this way, you now have 1, 2, 3, 4, 5 significant figures. So you haven't rounded to the correct number of significant figures. Okay. Okay, let's see. This is what I have here. And that's the answer. Now here they're just telling you once again the masses of all elements in the compound and the mass of the compound itself are directly proportional to each other, or they relate to each other. Okay, so they're saying here the question wasn't even provided until down here. Therefore, to find the mass of calcium fluoride that contains 3.55 grams of calcium, this is what we're going to do. Okay, let's do that from scratch, because I feel like they started in the middle. I'm like, wait, what happened? Okay. So what is wanted? Wanted grams of calcium fluoride that contain given 3.55 grams of calcium. Okay. To find the mass of calcium fluoride that contains 3.55 grams of calcium, we calculate. In other words, this is going to be our whole, right? Because it has all the elements. This is going to be our part. So we're going to do a part to whole relationship. But they didn't give us the relationship, so we got to find our own. Okay. Calcium fluoride. It has one calcium, has two fluorines, 2, 1. Each calcium is worth 40.08 grams. Each fluorine is worth 18.998, 19.0 grams. $40.08, and then here we got 2 times 19.0, which is 38 point, I guess 0 grams. Okay, add these two. We did this before, didn't we? Because I'm like, this is looking very familiar. 40.08. They recycle the same formulas. Anyway, 78.08 grams of calcium fluoride. There. If we need the total, this is the total. Oh, we're doing the calcium over calcium. Okay, so from this relationship, we can say calcium over calcium fluoride is technically 40.08 grams over 78.08 grams. Okay, so we have our relationship. Okay, I'm going to use the relationship I have here with the given number, and we will do our conversions. So I'm going to start with the given number. The given number was what? 3.55 grams of calcium. Let me zoom in. So we're converting this to figure out grams of calcium fluoride. So whatever number I put down here, the unit has to be grams of calcium. This is a conversion. I only have one conversion here, right? So, oh, this, you can say calcium here. You can say calcium fluoride to follow along, okay? So grams of calcium would be the top number, 40.08. Bottom number becomes the top number here. You have to flip it over, 78.08. These ratios here are a combo. They can go together if necessary, if they serve the purpose, or they can even be split apart. Calcium fluoride. Okay? Grams calcium, 3.55 times 78.08 divided by 40.08, 6.92 grams of calcium fluoride. Okay? Based on what I did, this is what I got. I didn't even look at their method. Let's see. Yes, look at that. Simply the best. Yes. Okay? This is what we get. Once again, the part to whole relationship can be used as a conversion factor. We did that here. Yeah, using a part to whole as a conversion factor. Do that here. They did it again over here in the mixture of all of this stuff here. The purpose of all of this was just to say there is a part to whole relationship and it can be used as a conversion factor. Okay, we're getting close to the end, y'all. We're getting close to the end. Okay, so before we get into this part here, quick summary. We now know how to go from a chemical formula. I shouldn't call it, let me just call it formula. We know how to go from a formula, right, to percent of elements. We are now about to do the reverse. to go from percent of elements to a formula. And this process is essentially figuring out the empirical formula of a compound. So we're told what the empirical formula is. Empirical formula is the simplest ratio of atoms of the elements in the compound. So once again, back to middle school, many years ago, we learned this, and for the most part, I was like, oh, I kind of like empirical formula chapter or section. I'm like, I think I like this one here. Okay, so just so that we can relate to it a little bit more, I'm gonna provide an illustration here at a page. So let's say we're looking at girls and boys in the class. I'm gonna use blue for boys, very traditional. 1, 2, 3, 4, 5, 6, and then girls. 1, 2, 3. And so I'm asked by my boss. So in your class, this by the way is my classroom. They're asking me, well, can you tell us the number of girls that relate to the number of boys? Or can you tell us a simplest whole number relationship between the girls and boys? And I can say, for every one girl, I have 2 boys. It's a relationship. It's a ratio that relates one to the other. Okay? So when you're relating one to the other, what you're describing here is the empirical formula. One number of elements as it relates to the other in the same environment. In this case, our environment will be my classroom. For every one girl, I have 2 boys, right? How did I know that? Count the number of girls. I have 3 girls. And how many boys? I have 6 boys. Okay? But they want a simple relationship. So this right here is a simple relationship that is technically the empirical formula. For every one girl, I have 2 boys. Now, there's something called the molecular formula, which we'll get to later on. But I want to define that here. When they tell you the molecular formula is also a relationship between in this case, the number of girls to the boys. But molecular formula actually provides the actual number. It's kind of like doing inventory in this case. In the molecular formula, you're trying to say, okay, how many boys are there? 6. Girls, 3. 3 girls, 6 boys. So molecular formula provides the actual number, of course, back to the chemicals, of atoms present in formula, right? Like you're taking roll. And of course, in my analogy here, that will be 3 girls and 6 boys. But if they say empirical formula, then you would say for every one girl, I have 2 boys. Or for every one girl, there are 2 boys. For every 2 boys, there is 1 girl. Okay? So hopefully you understand that. So in the context of the chemical formula then, most of the time they give you a molecular formula and they ask you to take the molecular formula and find the empirical formula. So let me go ahead, now that I'm done with this part here, let me go back to this slide, which says, when you're looking at the simplest ratio of atoms in the element, this is the empirical formula. All compounds with the general formula CnH2n have the same percentage composition by mass. FYI, okay, this is FYI, don't dwell on that statement. All subscripts are reduced to their lowest terms. So this is kind of telling you, how do you get the empirical formula? You're usually given a molecular formula. So let me go ahead and include this in here. I want a new fresh paper, so I'm going to write here. So you're given molecular formula, the one where you have every atom present that actually exists in the compound. Given molecular formula, comma, asked to find empirical formula. Ooh, empirical formula. This is what will happen. So we're told here all subscripts are reduced to the lowest terms. They have no common divisor. Okay. So if you're given a formula like this one here, molecular formula, I'll call it MF. This is going to be C4HA. What do? Now we're ready to read the statement here. All are reduced to the lowest terms. They have no common divisor. So find the greatest common factor between these two. Or I said 10 and I wrote 8. Between these two, the greatest common factor is what? Greatest common factor or greatest common divider. I've heard students say greatest common divider, so I'm going to write it like that. Is what? It's 2, right? 2, 2. So if you divide both of these by 2, we get C2H5. So you want to simplify this until it can't be simplified anymore, and then this becomes the empirical formula. So for every 2 carbons, there are 5 hydrogens. This is the empirical formula, simplest whole number relationship. Sometimes the molecular formula ends up being exactly like the empirical formula. Why? For example, if I give you a molecular formula that is C3H7, what's the empirical formula here? Well, is there a greatest common factor? The greatest common factor here is equal to 1. So the empirical formula is C3H7. They are the same. So they can be different if there is actually a greatest common factor that's not equal to 1, or they can be the same if the greatest common factor or the greatest common divider is 1. Okay? So let's go ahead and move on. So I really like the empirical formula determination once we learn it because it has steps. I realized I really like steps. Step 1, step 2, step 3, right? So here, step 1, determine the percentage composition by mass or mass of each element in a sample of a compound, okay? Step 2, convert the masses into the amount in moles of the atoms of the different elements. So you want to write this down. Step 3, determine the amount of ratio of moles of atoms. Step 4, express the amount of moles of atoms as the smallest possible ratio of integers. Step 5, write the empirical formula using the number of each atom in the integer ratio as the substitute in the formula. Okay, so we're going to go through step by step. I rushed through that because we're going to be doing step by step as I go through the steps. And then not only that, they have converted those wordy steps into a nice little table, okay? In a poem here, we're told a sample of pure compound is made up of 1.61. Okay, so I'm going to write this on the side so I can see. 1.61 grams. Okay, I need the space. Okay. Added page. Okay, we have a sample, and the sample is 1.61 grams of what? Phosphorus, and 2.98 grams of fluorine. Find the empirical formula of the compound. Okay, they're using theirs horizontally. I'm so used to doing mine vertically. You know what? Let me start vertically and I'll try to fill it in the table horizontally when I'm done. So let me do this. Let me copy this. Can I copy? Oh, hold on. I'm trying to get new school because I'm so old school, right? Traditionally, the way I learned it when I was younger in my days. But I'm trying to adapt to the way the book is doing it. This one here? Okay. So when I get done, I will put my answers in here. How about that? So we can reconcile old school with new school. Okay. So you have grams. So the steps usually are as we see listed here. For the most part, you have your element. Oops, here. Your element is what you're going to write first. After that, you're going to write your percentage. After that, you're going to have your mass. So right here, grams. You're going to have your moles. Then you're going to have your mole ratio. Mole. Ugh, I'm trying to leave out the E's. I'm telling you write it either way, it's fine, but I'm trying to graduate to writing, to leaving the E out. Why? I don't know, y'all. I'm obsessed with silly things. But I got element, percent, grams, moles, mole ratio. Then we have the, I'll say formula ratio. And then empirical formula. And when I'm done, I'm going to write this in the table. Okay, so let me see. I need to put my elements here to make sure everything fits. Phosphorus and fluorine. Okay, so usually this is the order. And most questions, they give you, instead of giving you the grams, they give you the percent. If they give you the grams, you have to start from where the grams is. They give a percent, start from where the percent is. So in this case here, they gave us the grams. So it's okay for us to skip over the percentage part. So I'll go straight to the grams and I'll write 1.61 and 2.8 grams. Okay? Because they didn't give me anything here, so I'm going to leave it as is. Now I have to get this grams and moles. So on the side note right here, moles equal grams over molar mass. Remember that this is periodic table molar mass? So I'm going to be doing that. To get the moles of this, I'm going to take this. Actually, I'm trying to think of a simpler way to do this. I'm just going to divide it here. Divide by molar mass, okay? Because I don't have a lot of room. The molar mass of phosphorus is 30.974 gram per mole, okay? So you can see here how gram divided gram and then per mole. This is a denominator of a denominator becomes a numerator, right? So my answer here will be 1.61 divided by 30.974, we get 0.051. 198. How about that? So I'm going to copy this down here. 0.05198 moles. Okay. On this side here, I take the grams of fluorine and divide it by what's fluorine? 18.998 grams per mole. And I end up with, this is supposed to be mole, right? I end up with 2.98 divided by 18.998 mole, which is 0.1568. Okay, moles. So I end up here with 0.156, I'll round it up, 9 moles. Okay, so now that we have this, when I divide, to get the mole ratio, I'll say here, divide by smallest moles. Okay, here you're taking, to get the moles, you're taking the mass over molar mass. Okay, that's how we're getting these numbers. Divide by smallest moles. So you take 0.05198 divided by 0.05198, and then 0.1569 divided by 0.05198. So divide by, let me get my number from up here, enter. What do I get? Here I get 3.02, and then here I get 1. So I'm going to round this up to 1 and 3 because the numbers after the decimal are 0.02. It's not a special number. If it was 0.33 I'm going to give that in a second. If it was 0.33, 0.25, I have to do certain things. For this one here, I don't. So let me see. So my empirical formula will then be, was P first, right? P, F, 3. Empirical formula. Ta-da! Okay. So how do I write this in here? Elements. I have to do it for both, right? Oh, they do it here. It should be okay. They do it here for me. Element P, F. Because I did it, but I'm like, here. Then moles. I mean, mass here. Then you divide by molar mass to get moles. Then divide by the least number to get the mole ratio. And then round it up to get that. And then you put in the numbers, subscripts. So these then become the subscript that produces that. Okay. I was gonna do it here, but I don't even have enough space. The bottom part is missing, but y'all see it over here, right? Okay, this problem here, this gives us the percentages. Okay. Now I did promise something. I have not forgotten. I did promise something. Let me see if I can delete this whole thing. Cut. Cut. Oh, I need to cut again. Cut some more. Cut again. Okay. So once you get to this part here in the formula ratio, let's say your formula ratio was like 1 and 1 point. Let me start with the simplest one, 2.5. Okay. And then, or it was 2 and 3.33. Or it was 3 and 1.5. 0, or it was 4. I'm just using random numbers. It doesn't have to be this big. It can be just 1 here. And 1 point, let's say 66. Usually the most common ones I've seen are these ones here. So let me stick with that. I was seeing 1.4. Anyway, because remember Dalton's law says atoms combine in whole. Think about what 0.25 is. 0.25 is 1/4, right? So to get a whole, to get subscripts that are whole, you want to multiply both of these by 4 by 4. And you will end up with, let's see. I'm going to use the same letters P and F just because I don't want to make up others. 1.25 times 4. So this is going to be 5. This is going to be 4. We'll end up with P4, F5. For this next one here, because it's 0.33, that's like a third, times 3 times 3. We end up with 6 here. We end up with 3.33 times 3. Oh, I said times 3 and I put, okay. It's going to be 10. So we end up with P6, F10. This one here times 2 times 2. To make this a whole number, you get 6 here. Here we get 3. This is going to be P6, F3. Okay? It depends on what. So these are called special decimals. If you end up with one of those quote-unquote special decimals, this is how you handle them. I'm using air quotes you can't see. This is how you handle those special decimals. If it's some number 0.25 or some number 0.35 or some number 0.50, you multiply it by 2 for 0.50, 3 for 0.33, 4 for 0.25. Okay, just FYI, because I don't get to do your homework problems, so I don't get to see all the challenges you guys face. Okay. Oh, this next one here. We're close to the end, guys. We're close to the end. Hang in there. Nicotine. Oh, this takes me back to organic classes, where nicotine is an amine compound, like a compound that has NH. Oops, you're not supposed to write with that. Like NH2 in it, or some kind of nitrogen in it. So nicotine is the brain stimulant, right? So most compounds that have nitrogen in them stimulate the brain, just FYI, just in case. Nicotine, it has carbon, hydrogen, and nitrogen. So let me write this out. Let me write this out just a little bit. Carbon, because I'm going to need to space between these, hydrogen, and nitrogen. And we're given the percentage here as 74.1%. Next, 8.64%. Last, 17.3%. Just like before, you have your percent here. You got your grams. You got your moles. You got your mole ratio. And then you got your formula ratio. And then you got your empirical formula. Empirical formula. Okay. So you want to go ahead and add the percentages. The percentages should add up to 100. Sometimes they give you all three. If you have three elements, they give you all three percentages. If they don't, and they tell you, well, one is missing, take 100 and subtract the other two percentages, and you get the missing one. Okay? So 74.1 plus 8.64 plus 17.3. So a little bit above 100. Did I get these numbers right? 74.2. Okay. Okay. 74.1, 8.64. Okay. I got a little bit above 100. That's fine. So if the percentages add up to about 100, then to get grams, just take percent and convert it to grams by replacing it. In other words, write it as 74.1 grams, 8.64 grams, 17.3 grams. Okay. To get to moles, you take 74.1 divided by carbon. Carbon is 12, right? This is gram. I'm going to do gram per mole here. 8.64 gram divided by 1 gram per mole. Nitrogen is 17.3 grams divided by nitrogen is what? 14 grams per mole. Okay. 74.1 divided by 12. 6.175 moles. It's going to be 6.175 moles. It's going to be 8.64 moles because the grams and grams cancel out. 17.3 divided by 14 is going to be 1.2. What is this? Oh, I wrote this earlier. That's okay. 1.236 moles. Okay, so I'm going to write this here, 1.236 moles, and then here is 8.64 moles. Okay, so to get the mole ratio, divide by the least number of moles, divide by 1.236 moles, we get 1, divide by 1.236 moles, so 8.64 divided by this top number here, and I get 6.99. And over here, this number divided by 1.236 moles equals to 6.175 divided by 1.236 equal 4.996. Okay, so my ratio then when I make these whole numbers is 5, 7, 1. So empirical formula will be, what was it? CHN, C sub 5, H sub 7, N sub 1. This is my empirical formula. I haven't run into one of those special scenarios. Okay. So in this last case here, they want us to determine the empirical formula of the compound and calculate the molar mass of the empirical formula unit, determine the molar mass of the compound, divide the molar mass of the compound by the molar mass of the empirical formula unit to get N and the number of empirical formula units per mole. Wow. Write the molecular formula. Okay, the idea here is um we went from molecular formula C, what was it again? C4H10, right? That was our molecular formula earlier. And from here, we got the empirical formula, which was divide by 2, C2H5. So obviously, these two are related to each other by this factor here, N, the greatest common factor. So what they're trying to say here in so many words, the greatest common factor N is equal to molecular formula mass divided by empirical formula mass. As in, to figure out what this divider is, if you get this mass divided by this mass, you will end up with the answer too. So this is what they're trying to say in so many words, right? That N is the molecular formula mass, which tends to be relatively heavier because it's actually taking an inventory of what's present, divided by the empirical formula mass, which is just doing this per that, right? That being the case, we're working on this problem here that says, no, I need the next slide. Add a page. A compound with the empirical formula C2H5. Look at that. Same one I was working with. So we told we have empirical formula. Oh, so imagine we've done all the work, right? And we've gotten the empirical formula EF as C2H5. And it has a molar mass. Molar mass. The molar mass is 58.12 grams per mole. They're saying find the molecular formula of the compound. So find molecular formula. Okay, we can do this. So remember, empirical formula is related to molecular formula if you multiply the empirical formula by that greatest common factor. Or I said earlier, the greatest common factor is equal to molecular formula divided by empirical formula mass. If you can get the mass of the molecular formula divided by the mass of the empirical formula, you actually get what N is. And once we solve for N, and we know what N is, we can multiply the empirical formula by N to get back our original molecular formula. Okay, so how do I do this? There's really no mystery here. The mystery here is molar mass is the same thing as molecular formula mass. Remember that 1 million, it wasn't really 1 million, it was like 3 different ways of describing the same thing. Molar mass is the same thing as molecular formula mass. So in this equation here, we already have the top number. We need to find the bottom number. What is the empirical formula mass? So what is the EF mass? Well, to figure out the mass, you need the formula. What's the formula again? It's C2H5. Okay. How many C's do we have? We have 2. How many H's do we have? We have 5. Each C is what? 12. I'm going to use approximations here. Each H is what? About 1. 2 times 12, 24. 5 times 1, 5. Yeah? Okay. Total, 29. Oh, so I have the mass for this. Look at that. Look at that. Grams. What unit did they use here? Grams per mole. I'll say grams per mole. I'm adapting. You see how I'm adapting? Grams per mole, grams per mole. So I'm going to use grams per. I was in a row and then I just grams per mole. Okay. So let's see. What are we doing here? Trying to find N. N is going to be molecular formula mass. I just copied the number they gave me right here. Just copy that. 58.12. No, don't freeze. No. We've been together. Oh, okay, let me see. Ah. Okay. Let me see if you come back to working. Yeah, when your computer is tired. Okay, I'm almost done. I'm almost done. You see the slides? I'm just one slide away from being done. Okay, molecular formula mass 58.12. 58.12 grams per mole divided by 29 grams per mole. What do we get here? The units cancel out. 58.12 divided by 29. This gives us exactly 2. Okay? So essentially, what do we have here? So if you take the n we just solved for and multiply it by the empirical formula, we get the molecular formula. Our empirical formula is, so it's 2 times C2H5 equal C4H10. Look at that. You're multiplying the number by the subscripts. That's it. So this is our molecular formula right here. Molecular formula. Ta-da! And that's the end of that. Okay? So I'm thinking, oh, okay, y'all don't judge this right here. Don't judge this. Okay, I was struggling to post this up there, and then stuff happened and stuff happened. Anyway, this is the end. This is the end. Today I faced a lot of challenges, but I'm glad I am done with this chapter. Tomorrow we will do chapter 10. That will be the last chapter. And yeah, that will be the end of this. So let me see. Let me stop recording.